This is a special kind of a compound where you have all the carbons in a ring or a loop, and you have alternating double single bonds. Now, at first, this might look like a cycloalkane, but it's more than that because you have double single bonds. It might also look like an alkene with double bonds, but we're going to see that this is a whole nother group altogether. So what this is an example of is what's called an aromatic hydrocarbon. An aromatic compound is when you have double bonds that can resonate. They move literally from left and right around the track. Now notice that this is a flat structure. All right, all of the double bonds are above and below this six-ring structure, and they do literally move around. They resonate around. So sometimes what people will do is they'll draw that circle in the middle right there. That's the fact that represents how these kind of compounds, that resonance makes the double bonds go round and around and around and around. So aromatic compounds are amazing. They're almost like science fiction to me. It's so weird. They're flat because those double bonds that resonate go back and forth, and they're very, very stable. And there's actually a whole bunch of these aromatic compounds, but I want to focus here on benzene, which is the simplest of the aromatic compounds. Benzene gets the formula C6H6, and that's what we see rotating right there. Again, benzene is amazing. It's not quite an alkene. It's not like a cycloalkane. It's a whole other kind of compound, and it has a completely different reactivity to it. Benzene is pretty amazing. These are three different views of benzene. The upper left one is what we call the sigma network. Those are the single bonds that connect the carbons to the carbons to the hydrogens, all that kind of jazz. But check out the lower left-hand one. That's the pi network. And you can see it's like two donuts, if you will, like one on top of the other. All those pi bonds, those double bonds and the pi bonds, they're resonating, all right? They're delocalized. They're not just between two atoms. They're actually connected to all six atoms. So it creates, if you will, like a force field above and below the sigma network. So when you put them all together in the upper right, that shows the sigma and the pi bonds. It's amazing, all right? Delocalized just means that instead of having double bond between two atoms, the double bonds literally resonate around the molecule. It's like a racetrack. And again, I said shields around the sigma network. That's not too bad of an explanation. And that's why these things have their own like reactivity. They're totally cool compounds. In a normal compound, a carbon-carbon single bond, about 154 picometers, and a carbon-carbon double bond, roughly 134 picometers. Well, in benzene, you have 139 picometers. So notice it's certainly not single bond length. It's a lot shorter, but it's not quite double bond length. And we talked briefly earlier how as bond order goes up, the bond length goes down. So that's why a bond order 2 double bond is shorter than a bond order single bond. So 134 is shorter than 154. Well, carbon-carbon bonds in benzene aren't doubles or singles. It's more like 1.5. It's kind of in the middle. And you can see it's actually close to a double bond. This is a very stable molecule. So instead of being a single or a double, we would say the CC bond order in benzene is 1.5. But it's probably closer to 2. This is so stabilized because of those pi electrons that are kind of floating like donuts around the molecule. Benzene's amazing. You'll talk a lot more about this in organic chemistry, but I just wanted you to hear this and kind of hear these terms so that you'll be good to go and be able to figure it out. You can put pieces on the benzene molecule, and these are just different examples of them. Probably the most famous of all of these is this one right here. The official name is methylbenzene. It's a methyl group off the benzene ring, but people call it toluene. You can buy toluene at Fred Meyer's. It can be used as a paint solvent, all kinds of different things. All these other names are maybe things you've heard of before. Nitrobenzene. Nitro is an NO2 group. Benzoic acid is actually a COOH. We'll talk about that a little bit. Once in a while you hear about phenol. I was listening to a movie the other night and they actually said phenol a couple times. I was like, Anyway, phenol is an OH group of the benzene. And you can also put the benzene groups together. And that's what this naphthalene thing is. It's like two benzene rings kind of fused together. And you can have halogens, bromobenzene. You can have alkyl groups off benzene, ethylbenzene. Lots and lots and lots of possibilities. If you have species on the benzene ring that are the same, you end up with another kind of nomenclature I want to introduce. In the old days, they called them ortho, meta, and para. And ortho means that the two groups that are the same are right next to each other, like 1 and 2. Now on benzene, you have a total of 1, 2, 3, 4, 5, 6 places they can go. So if the two similar pieces are next to each other, like 2 chlorines or 2 bromines or 2 methyl groups, whatever, then that's called ortho or just O dichlorobenzene. But I would prefer that you use numbers for it so no one's confused. 1, 2 dichlorobenzene would be an alternate way, but you will see ortho used a lot or ortho dichlorobenzene. Either one is fine. Now, if the species are there's like a carbon between them, like that carbon's between this one and this one, then it would be a 1,3-dichlorobenzene, but people will call it meta-dichlorobenzene or just M-dichlorobenzene. And finally, para means 1, 4. They're literally 2 spots away. 1, 4 would be 1,4-dichlorobenzene in this case, or para-dichlorobenzene. Now, if you're thinking, why isn't there a 1,5-dichlorobenzene? There absolutely could be, but if you think about it and you number instead of left, like going clockwise, if you go counterclockwise, you'll see that 1,5 would be actually the same as 1,3-dichlorobenzene. So again, you can number these things in both ways. I'm talking about them here in clockwise fashion, but you should think about what they would be in a counterclockwise fashion as well. All of the families of compounds we've looked at so far have basically been true hydrocarbons, carbon and hydrogen only. I did throw in some halogens because that seemed appropriate, but everything else has been just carbon and hydrogen. However, there's no reason to have just carbon and hydrogen. You can also throw in other atoms, for example, oxygen. And oxygen, if it's placed on a carbon-hydrogen part, can also create some new classes of compounds. So probably the most common kind of oxygen-containing organic chemical is what's called an alcohol. Now, alcohol, a lot of times people think is drinking alcohol, and we're going to see that is one of the chemical alcohols we're going to talk about here in a little bit. But an alcohol really is nothing more than an organic chemical that has a hydroxyl group. Hydroxyl is an OH group. Now, oxygen, if you remember from Lewis structures, it likes to have 2 bonds and 2 lone pairs. So a hydroxyl has 1 bond to hydrogen and then 1 bond to connect to something else. And you can take that hydroxyl group and connect it to an alkyl group that creates ROH, and that's what an alcohol is, the generic representation. So there's the formula for an alcohol. Notice it's like an alkane with an oxygen on the end, no worries. And to name it, you take the YL off the alkyl group and add anol. So in the lower left-hand corner there, that's ethanol. That's drinking alcohol, by the way, the one that gets people drunk and stuff. But anyway, to name it, ethyl is the 2-carbon alkyl group. Take the YL off to have eth, and then add anol, ethanol. CH3CH2OH is ethanol. Ethanol is more than just drinking alcohol. It's actually a great solvent for a lot of things in organic chemistry as well. There's a new way to name organic chemicals with alcohols. This is mostly appropriate when there's a choice where the alcohol goes. So back in the day, I would call 3 carbons with an OH off one of the end carbons, I would have called it 1-propanol. But the new way of calling it is to put the number next to the OL, similar to what we did with the alkenes, but in this case it's alcohols. Propan-1-ol would be the new way, and I don't care if you call it 1-propanol or propan-1-ol to me, but just realize they're both out there. And this is important because you could put the OH off the second carbon. So in my day, I would have called this 2-propanol, but the new way of naming this then would be propan-2-ol. These are isomers of each other, and you bet you start seeing a lot of isomers here when you start getting to alcohols and basically 2, 3 or more carbon atoms. If you take organic chemistry one day, this is going to be something important to you. I won't ask you any questions, and if you're not taking organic chemistry, you can kind of zone me out. But they talk a lot of times about primary, secondary, and tertiary alcohols. A primary alcohol is just where you have an OH, and there's only one carbon connected to the carbon that you have the OH on. Now, I'm sure that was as clear as mud. So let's look down here at ethanol. It's a carbon with an OH, so it's an alcohol, and this carbon has one carbon connected to it. So that would be an example of a primary alcohol, all right? The carbon with the OH has just one carbon next to it, primary. On the other hand, a secondary alcohol, all right, would be something like the middle one right there. So if you look in the lower part, this carbon is connected to an OH, so it's an alcohol, but that carbon has not just one, but two carbons connected to it. So that would be an example of a secondary alcohol. And you nailed it. If the carbon with the OH is connected to 1, 2, and 3 carbons, that's going to make it a tertiary alcohol. The reason this is important is each of those methyl groups donates electron density, and so the effects on the OH are quite drastic. And on the right-hand side are just some more examples. If you never take organic chemistry, don't worry about it. But if you do take organic chemistry, just realize this will be something coming down the pipeline to you. So here's a question you might see. It says, what's the name of this molecule? Okay, first thing to do, like always, count up your longest chain of carbon atoms. 1, 2, 3, 4 carbon atoms. That's going to be butane if it was an alkane. This is not an alkane, though, because one of the hydrogens has been replaced by a hydroxyl group, the OH, which makes it an alcohol. So butane as an alcohol would be butanol, and you think you might be done. But that OH doesn't have to be off that carbon. So for example, you could move it to the right one spot. That would be a whole different alcohol. All right. So we're going to need a number associated with it. So in the old days, what I would have done is I would have counted left to right, right to left. And I'm hoping you're getting better at this. If you count right to left, that OH is off the second carbon. So I would have called it 2-butanol because the OH is off the second carbon. But in this new way of doing things, the 2 goes right before the OL. So butantuol would be the new name of doing it, and that's fantastic. If you want to get into the type of alcohol, the carbon with the OH is connected to a CH3 on the right and an ethyl group CH2CH3 on the left. It has 2 carbons. That would be a secondary alcohol. Don't worry about it, as I said, in this class, but in future classes that might be important. You can have 2 hydroxyls, 2 OHs off the molecule as well. And this creates what's called a glycol. A glycol is a diol, 2 alcohols. All right, they have 2 OH groups on them. And they're actually somewhat similar. Ethylene glycol and propylene glycol are both used as antifreeze in your car. Now, the official names would be ethane 1,2-diol, propane 1,2-diol, but a lot of times they just call them ethylene glycol and propylene glycol, and that's fine. Glycerol is an example of a compound with 3 OH groups. So propane 1,2,3-triol would be a fancy name for it, but people usually just call it glycerol. Glycerol is the same as glycerin, same name. Glycerin is the common name. Glycerol is a little bit more fancy chemistry name. And I've got some other triols down there that are available. So anyway, just realize lots of possibilities in organic chemistry. But again, if you break it down, longest chain, that's going to be alkyl, butane, octane, that kind of stuff, and you put these other substituents on it, good to go. Ethers are oxygen-containing organic chemicals as well. But while alcohols had the hydroxyl, the OH group, ethers are oxygens with carbons on both sides of them. So in the bottom down there, you can see the red oxygen atom, and there's ethyl groups on both sides. Ethyl is CH2CH3. So no problem, just another type of organic chemistry compound. Now in the old days, we used to call these alkyl-alkyl ethers. ethers or dialkyl ethers. And what I mean by that is if you look at that one in the lower left again, alkyl is the ethyl group on the left, alkyl is the ethyl group on the right. Two ethyl groups would be diethyl ether. And that's what almost everybody calls that compound, just so that you know. And if you use this old school version, in the upper right hand corner, you've got two methyl groups connected by an oxygen. So that's an ether. The oxygen's between two carbons, dimethyl ether. On the other hand, the lower right there, you've got an ethyl group on the right of the oxygen and a methyl group on the left. Alphabetical order, you know how this rolls, but anyway, you'd call it ethyl methyl ether. So when it says alkyl ether, that's what it means. Ethyl methyl ether, spaces between them. If they're the same, then you can use dyes. But this is old school, and my students were able to tell me that, yeah, you should really start talking about the new version of ethers. Okay, no problem, and I'll admit it is kind of cool. So the new way, the IUPAC way, it's the shorter alkyl group, and you have an oxy added to it, and the longer alkyl group you call as an alkane. Okay, so I'm sure that was pretty standard and easy to figure out. Let's look at that little picture right there. This little ether, by the way, it is an ether because oxygen's in the middle of carbons. On the right side, there's two carbons. That would be an ethyl group. And on the left side, you have 1, 2, 3 carbons. That would be a propyl group. So the shorter alkyl here would be the 2 carbon group. That would be an ethyl group. But we're going to take the YL off and put an oxy on it. So that little group right there, the entire OCH2CH3, that becomes an ethoxy group. And on the right-hand side, 1, 2, 3 carbons, we're gonna call that a propane. That's what that means. Take the YL off and add ANE. Now, when you're doing this, you need to tell where the ethoxy group is connected. And in that picture, the ethoxy group is connected to the first carbon of propane. 1-ethoxy propane would be the name of that crazy thing. Now, in the old days, we used to fumble and call it ethyl 1-propyl ether, which works, but on the other hand, I kind of like the 1-ethoxy propane, so that's why I'm pushing it here. So shorter alkyl group gets an oxy, longer alkyl group gets ANE. And if they're the same, then you can just one or the other, doesn't matter. Here's 2-ethoxy propane. So this is also an ethoxy, an ethyl group, C2H5 with an oxygen, but it's connected to the second carbon of 3 carbons in propane. So that's why it's 2-ethoxy propane in that one, or ethyl 2-propyl ether. And what the heck, let's do another example. This is a methoxy group. It's a methyl group connected to oxygen. The methoxy group is in the middle of those 3 carbons, which is a propane, 2-methoxy propane. So you can see in the lower left-hand corner, you either get organic chemistry or you don't. It's an organic chemistry joke. Anyway, I have a coffee mug of this in my office, kind of embarrassing. But anyway, ethers are cool. A lot of cool things you can do with them. Realize there's 2 naming systems. Good to go. All of the oxygen we've seen so far have had 2 single bonds. So like, for example, a single bond to the hydrogen for the hydroxyl and connected to the carbon on the other side, that made the alcohol. On the other hand, if oxygen was connected to 2 separate carbons, that made the ether. Well, you don't have to have the oxygen connected to 2 separate carbons. You can put them both on the same carbon. So this introduces what's called a ketone. And a ketone is a carbon-oxygen double bond. Now, carbon-oxygen double bonds in organic chemistry are called carbonyls, and they're a really cool source of energy for organic chemicals. And you'll talk a lot more about carbonyls in the compound. So in this particular section, if your carbonyl, that C double bond O, has carbons on both sides of it, that's what creates a ketone. So in the lower left-hand corner, the carbonyl is that thing right there. It's a carbon-oxygen double bond. And to the left and the right, you have methyl groups, CH3. So it's a methyl group, a carbonyl, and a methyl group. But important for us right now, the carbonyl has carbons on both sides of it. That's what a ketone is. So to name a ketone, count up the total number of carbons, including the carbonyl carbon. So in this case, that would be 3 carbons. As an alkane, that would be propane, but since this is a ketone, we're going to call it propanone. propanone is the name of that compound. And in the upper right-hand corner, if you count up the carbons, there's 1, 2, 3, 4. 1 for the methyl, 2 for the carbonyl, 3 the line, 4 that methyl, 4 carbons, butane becomes butanone. The last 2 you need a number because you could have a 2-pentanone or a 3-pentanone. Nothing you can't handle. However, propanone deserves some comment. Propanone is actually known as acetone, and we've used this in lab several times. Acetone is a great way to make wet surfaces dry. It's also used to remove fingernail polish and lots of other kinds of uses. Acetone, again, is the common name. Propanone is the more serious chemistry name. Both names are great. You now know that they're ketones. Aldehydes have a carbonyl as well, but aldehydes are different from ketones because on at least one side of the ketone you have a hydrogen. And for reasons which I cannot go into right now, but you will in organic chemistry, having that hydrogen there affects the reactivity in a huge way. So if you have a hydrogen connected to the carbonyl, that's what an aldehyde is. So an aldehyde will have a hydrogen on one side of the carbonyl. The other side could be a second hydrogen, like in the lower left, or it could be an alkyl group, doesn't matter. But anyway, aldehydes are different reactivities, which is crazy. Now, aldehydes have Al, and that's the name you want to give to the aldehyde. So you name it like it's an alkane, take the E off and add Al, or you can do what I do up there in the description. It's an alkyl group without the YL, and you add ANAL off to it. Anyway, so butane becomes butanal, and ethane becomes ethanal in the lower right-hand corner. Ethanal is also known as acetaldehyde. That's something you'll hear about later. But anyway, methanal is the simplest one. It's a carbonyl with hydrogens not on just one side, but both sides, which is totally fine. Methanal has a more common name too, formaldehyde. Down in the funeral services area of Mountain Community College, they use a lot of formaldehyde. Formalin is formaldehyde in water. That's the little compound right there. It's a great preservative of things, stuff like that. So let's name this compound right here, all right? And as you can see, this compound has 1, 2, 3, 4 carbons, so it would be like a butane. However, it has a carbonyl, a carbon-oxygen double bond. So if it has a carbonyl, it's going to be an aldehyde or a ketone. And to make that decision, the carbonyl, the carbon-oxygen double bond, does not have a hydrogen next to it. That carbonyl has a CH3, a carbon on the left, and a CH2, CH3, another carbon to the right. So if there's carbons on both sides of the carbonyl, it's a ketone, and a 4-carbon ketone would be called butanone. So this answer for this molecule would be butanone. If it was butanal, it would have a carbon-oxygen double bond on the N carbon, and there would be a single hydrogen connected to it. But this carbonyl has carbons on both sides. It's a ketone. A carboxylic acid also has a carbonyl, a carbon-oxygen double bond, but instead of having a hydrogen like the aldehydes do, it has a hydroxyl group, an OH. So these have C double bond OH groups on the very end. And this is a real reactive little area for things. All of the carboxylic acids are weak acids, and they have reactivities which are very, very similar to each other. So here are just some examples of these different things. To name them, like in the lower left-hand corner, count up the total number of carbons. So this one has 3 carbons, 1, 2, 3. Propyl would be the alkyl group's name, but you take the YL off and you add anoic acid. This would be propanoic acid, all right? And if there are 6 carbons, like there are right here, that would be hexanoic acid, methanoic acid, which is also known as formic acid, by the way. You can have different groups. Now, the carboxylic acid is always going to be carbon number 1. So you always want to start with number 1 right there. So in the lower right-hand corner, the carbon with the carbonyl is number 1. The methyl group is off the 2nd carbon. That's why it's 2-methyl butanoic acid, stuff like that. Acetic acid is probably the most common carboxylic acid. Acetic acid is the active ingredient in vinegar. And acetic acid, which is officially ethanoic acid, if you call it by its official name, very, very common. We've been talking about CH3C double bond OOH for a long time. Benzoic acid is another popular carboxylic acid. It's a benzene ring with a C double bond OOH. And even aspirin has a carboxylic acid group on the end of it. Right up here is a C double bond OOH group, and that's why it's considered a carboxylic acid. It has another functional group right here. This is a C double bond O with carbons on both sides. That's another group. I'm not even going to introduce it right now, but just realize there's a lot of things to do in organic chemistry. No problem. But anyway, carboxylic acids are all weak acids. They're almost always in the foods and drinks we consume. So breads and fruits and wines, almost everything we eat is slightly acidic. Not too acidic, but a little bit acidic, thanks to the carboxylic acids. So let's say we wanted to name this compound. I would start by counting the number of carbons. 1, 2, 3, 4, 5 carbons. That would be pentane if it was an alkane. But this is certainly not an alkane. We have more than just CH bonds. This has a C double bond OOH on the end right there. And that makes it a carboxylic acid. So 5 carbons pentane as a carboxylic acid, it gets an oic acid ending. This will be pentanoic acid. You don't need a number for carboxylic acids. Number 1 is always the carboxylic acid. It's the more exciting part of the molecule for chemists. All the other carbons are more boring, but this is how that rolls. An ester is a group I will not ever ask you a question on how to name it, but I really want to introduce it because on a quiz, I thought ester and ether were the same. Not even close. Ethers are carbons with an oxygen in the middle and another carbon on the other end. An ester is a carbonyl, C double bond O, with an oxygen, and there's an alkyl group on both sides of it. So you can see in the lower left right there, we have an ethyl group on the right, and then the 4 group on the 5 carbons on the left would be a pentyl group. So to name these crazy things, the smaller one is listed first, and the longer one gets an O8 ending like that. So that would be ethyl pentanoate. And in the upper right-hand corner, the methyl group is smaller, so methyl first, ethanoate, etc., etc. You don't have to name these, but if you see the O8 ending or you hear ester, just realize this is a whole separate family. And there's a lot of really neat things you can do with esters, but I'm going to let you wait until organic chemistry to really figure out how these all run. I need to talk briefly about nitrogen in organic chemistry compounds as well. Nitrogen is another player when it comes to organic chemistry, and the simplest of the nitrogen compounds is when you take off one of the positions on nitrogen and put an alkyl group off of it. Now, if you remember from Lewis structures, nitrogen is happiest with a lone pair and 3 single bonds, all right? So you can take 1, 2, or all 3 of those bonds up with alkyl groups. And that's why you see that weird system right there. So the number of alkyl groups, it can be no more than 3. And if you have less than 3, then you'll replace them with hydrogens. So let's talk about one of the simplest families of alkyl groups, which are listed in the upper right. The first one is methylamine. The nitrogen, which is in blue, has 1 methyl group connected to it, and the other 2 spots on nitrogen are just taken up by hydrogen. There's a lone pair on that nitrogen right there. It's going to give nitrogen its distinctive reactivity and stuff. That would be methylamine. But the next one to the right, that nitrogen has 1 hydrogen and 2 methyls, so it's dimethylamine. And finally, you can replace all of those hydrogens with alkyl groups, i.e. trimethylamine. Very, very cool. In the lower left-hand corner, that animation is for ethylamine, 1 ethyl group connected to nitrogen. These amines have nasty, nasty odors, and I never recommend that you are around amines if you can help it. Honestly, most of the amines are weak bases, and that's why they're really good about cleaning things. We're not used to smelling them and stuff, which is crazy. An amide is something I will never ask you any questions about, but I want you to hear this name because amide and amine sound really similar, and honestly, on a quiz, I thought amide was the same as an amine, and I didn't do too well. So So anyway, if you hear amide, the name, or even better, if you see the capital N, like right there, that means that you've got an amide. And an amide is another nitrogen compound. It's got some kind of alkyl group next to it, but it also has a carbonyl. And if you put that carbonyl, that C double bond O, next to the nitrogen, you have all kinds of reactivity issues. So just realize this is another real powerful kind of condition. In the lower right, you see an NN dimethyl. That's because the nitrogen has two methyl groups connected to the nitrogen. There's a lot of stuff you can do with it. And again, I'm not going to ask you anything about this, but I want you to know that an amide is different than an amine, and that's important to me. This is an overview of the different families we've seen. So we've seen, for example, how a double bond between two carbons is an alkene, triple bonds alkyne, alcohols and ethers, aldehydes and ketones, carboxylic acids. Ester is one I'm not going to ask you about, but I want you to know. Amine, the nitrogen groups, and amide, which is another one I won't ask you to know, is the nitrogen connected to the carbonyl. Alkanes are the simplest ones, so don't forget those. Those are just carbon-carbon single bonds, and they're also really important. So again, if you kind of understand how this works more or less, that's what I want you to do. And I definitely want you to know about alkyl groups and how they're the building blocks of all these things, and definitely know that amide and amine are different, and ester and ether are different. You're in good shape.
To visually reinforce the fact that members of a homologous series, such as we see here, differ from each other by a specific structural unit, we use molecular models. Here, for instance, is the tetrahedron of carbon, a model of methane. In order to turn that model into ethane, we add another CH3 group to the end by substituting for a hydrogen. If we wanted to go from a propane to an ethane, we would remove that specific member of the homologous series, a CH2 group. Reconnecting the carbon atoms, then we're back to our ethane. Models can be used that are commercially available, but if they're not available, gumdrops work just as well.
If you take organic chemistry one day, I would find it essential, all right, not recommended, but essential that you purchase a model kit, all right, because as you can tell, there's lots and lots of different structures, and each structure has its own variations. Those different variations will have their own geometry, which leads to differences in reactivity, and it's really, really cool to have a model set. At the time of my making this video, the model kits are roughly $20 on Amazon. You can get any of them that work, but wow, they can sure be helpful. So again, I highly recommend it. And in addition, all of those cis-trans things with double bonds, those can get kind of weird. The model kits will help you out. Eventually, you'll get into the chirality, like the mirror images we talked about in chapter 19. And oh my goodness, the model kits are so invaluable. So highly recommended. And yes, you can use gumdrops, but I intended to eat all my gumdrops, so I never had my good model kit. So I finally just bought one so I wouldn't have to eat them. But anyway, that's a personal thing. So there we go, off my high horse. I've told you what I think. Okay, the remaining slides in this chapter are just informational. I want to give you some examples of reactivity, and I'm not going to ask you any questions on this in Chem 223. However, if you go into organic chemistry, you'll kind of get an idea as to what you're going to get yourself into, and it's totally doable. It's just kind of crazy. Reactivity is, of course, a much bigger part of the chemistry, the organic chemistry year, but it's all stuff you can do. I'm also going to talk real fast about polymers. Polymers are plastics, all right? And that's another really important part about the world and organic chemistry, but everybody tends to gloss over, which is unfortunate. So the rest of the slides, you can just stop now and, go watch TV or something. But anyway, or you can go on and learn more about this stuff. Either way is cool. This is a background picture that my son took when he took organic chemistry, and it shows some of the reactions that he was studying. And I am just amazed by this picture. I look at it and just like, whoa, so cool. But anyway, this is an example of reactivity. And reactivity is huge, all right? Because you have to know, first of all, how to make the compounds that you talk about. And then once you make them, what do you do with them? So both reactivity in making them and in reacting them, really, really important. So we're not going to go through any kind of detail here as to reactivity, that's for sure. This is what most of the year of organic chemistry is all about. But we will look at some patterns. I want to give you some examples so that when you go in, you'll at least know a little bit about some of the things you might see. The first type of reaction we're going to look at is called an addition reaction. And an addition reaction is when you have a double bond, sometimes triple bonds, and you're going to add a diatomic. Now remember in the back of your mind that carbon likes to have 4 bonds. Well, if you have a double bond, say, then what's going to happen in here is that the double bond will be broken, but carbon still needs to have 4 bonds. So the diatomic, the 2-atom system, like bromine here, one bromine's going to add to the carbon on the left and the other one will add to the carbon on the right. So you can turn an alkene, the double bond, into an alkyl halide, the compound on the right, 1,2-dibromoethane. And you don't have to use bromine, you could use hydrogen, so you could turn the alkene into an alkane. You could add like HCl, so hydrogen would go on one side, chloride on the other. You could even add water, you'd have hydrogen on one side and an OH on the other, which is pretty cool. So this is an example of an addition reaction. You're adding a diatomic across a double bond.
Molecules of bromine gas undergo an addition reaction with the carbon-carbon double bonds in bacon fat, causing consumption of the bromine gas.
There's lots of interesting reactions associated with addition reactions. And again, there's a lot more to it than we're going to talk about here, but you get the idea. And remember in the back of your mind, carbon likes to have 4 bonds. So you break the double bond, you add 1 atom to each side, you are good to go.
Atoms of hydrogen gas undergo an addition reaction with the carbon-carbon double bonds of propene, changing the molecule into propane.
This is just another example. You're taking an alkene, a carbon-carbon double bond, and turning it into an alkane, all single bonds, using H2. So again, when you break that double bond, you have to have something on each carbon. That's where the diatomic comes in. One hydrogen adds to the left, one hydrogen adds to the right. You're turning sp2 carbons, double bond carbons, into sp3, all single bond carbons. Kind of cool. You can take a fat and hydrogenate it with hydrogen, and this is something sometimes they'll talk about in the food industry. If you look on labels, sometimes you'll see partially hydrogenated oils or fully hydrogenated oils, which I call malarkey on. Anyway, what they're trying to do is they're trying to take those double bonds, which could be cis or trans, as we talked about earlier, and they're trying to make them all single bonds. I would be very careful to not consume too many hydrogenated vegetable oils if you can. I don't think the efficiency of those reactions is 100%. Like, I don't think you have all the double bonds transferred. And if you had some cis, they might turn into trans bonds, which are really bad. So be careful of those. They're a little bit freaky. But at least now you know the chemistry behind them and you can decide what you want to do after that.
In the substitution reaction of glycerol with nitric acid, hydrogen atoms on the glycerol are replaced by the nitro group to produce nitroglycerin and water.
Nitroglycerin is a super reactive compound. You have to be super careful moving it around. And what they do is they start with glycerol or glycerin, same thing, and it has 3 OH groups on it. And if you add essentially nitric acid, the NO3 group attaches where the OH group was. The OH is kicked off. That's what makes the nitroglycerin. And again, it's easy to have that be a contact explosive. That's why I like showing that little video right there. But anyway, this is an example of a substitution reaction. You're replacing an OH with a nitro group, the NO3 group in this case, and it makes a brand new kind of compound. Glycerin is easy. You could store it in a bottle. Nitroglycerin, you want to be super careful of. It's very, very unstable, so you have to be very careful with it. Different reactivity, different compounds.
In the reaction of 1-propanol and sulfuric acid, a hydroxyl fragment is eliminated from the 1-propanol to form propene.
If you have an alcohol and you add a little bit of H plus acid to it, the H plus reacts with the water. H plus, by the way, is kind of a catalyst, doesn't really react. But anyway, it ends up turning the alcohol into an alkene. So this is a way to go from an alcohol to an alkene. You just add a little bit of acid to the OH, and it comes off then as water, and you end up making an alkene. So this is pretty cool. So you can see what we've done here. You can use an elimination reaction to turn an alcohol into an alkene, and you can then use an addition reaction to turn that double bond, say, either back into the alcohol or into a dibromopropane or something like that. Lots of different possibilities are available to you once you understand how these mechanisms work. A polymer is a science term where you take many, many small pieces called monomers or just mers, and you put them together. So you have many, 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 many repeating. So many pieces together would be polymer, many of them put together. And polymers are what plastics are, and many other things as well. But I think it's important to talk about polymers because, man, our species uses so much plastic. And roughly in the United States, each person that's alive, 150 kilograms of plastic is made per person, all right? And wow, that's a lot. So this is a huge, huge part of science that isn't discussed a lot in this level, and I honestly think it should be. But anyway, if you need to make your plastics or you need to make a polymer, you just take many small parts and you combine them together. And they're combined usually into many things which are around us all the time. The molar masses of the polymers are usually huge. So 10 to the 6 is a million. Often the polymers will have tens of millions grams per mole. So I mean, just massive molecules. And again, a lot of our fabrics, Teflon, use these kind of things. Lots and lots of uses for polymers. So what we're going to do is just look at two of the main ways they make these polymers, which are called addition and condensation reactions. And one day, if you take a polymer course, which, believe it or not, I have done, it's fascinating. It's a massive part of our economy, and it's a massive part of society. And of course, cleaning up plastics can be an issue. We're not going to go into it now, but anyway, just think about these things as we go through this section.
Addition polymerization begins when an organic peroxide produces free radicals. These can react with a monomer to produce another free radical. This unstable intermediate can react with a second monomer to form a larger species. Eventually, a polymer chain grows. The chain can grow to contain many thousands of monomer units. A termination step seals the reactive end of the growing chain. One possible termination is the coupling of two chains.
An addition polymerization reaction usually involves a peroxide. Peroxide have oxygen-oxygen single bonds, which are pretty unstable. They both want to pull electrons away from them. So the peroxide breaks up, you end up with a paramagnetic piece, and that attacks usually like something like ethene, which is a carbon-carbon double bond. And that paramagnetic part attacks the pi bond. It makes a single bond, but then in the process, it makes a paramagnetic end on the other end of the ethene, and that paramagnetic part goes on to react with another ethene to make a new paramagnetic part, and it goes on and on and on and on and on until finally you get two paramagnetic heads that kind of come together to make a single bond, and that stops the process. But a lot of these will have like 300,000 or more units coming together to make these long chains. So the molar masses are just crazy, like a million or so. Pretty wild stuff, and it's amazing that they work together like that. This is an example of a polyethylene synthesis. And so what they do is they take a peroxide. This is benzyl peroxide. Notice that there's an oxygen-oxygen single bond in the middle. And if you just heat these things up, they usually break up. And in the process, they tend to make a paramagnetic center. So if you look really carefully right there, there's a little black dot. That's the odd electron. That's the paramagnetic part of this. And one benzyl peroxide will create two benzyl methyl radicals is what they call, and each of those can go on to react with other pieces. So in this case, this is an ethylene molecule, H2C double bond CH2. That's ethene officially, but they call it ethylene a lot. Anyway, it attacks one of the ethylenes to make this species, and you can see that dot was just pushed over to the end. That's a new paramagnetic species, and that can go on to react with further ethylenes and stuff, make more and more and more, until finally you get to the end where two paramagnetic species come together. They make a single bond, and that stops the reaction. So the little N down there, that's common for these kind of reactions. N, again, could be like 300,000 or more. They're just massively long species, and that's what creates then polyethylene in this case. There's different types of polyethylene. If everything is long and in a nice chain, they call it linear high-density polyethylene, or HDPE. But you can also have low-density polyethylene, LDPE, cross-linked polyethylene, CLPE. All of these things are pretty common. HDPE and LDPE are fairly common in our day-to-day life, as I'll talk about in a little bit. Polystyrene is a non-polar material. If you ever use those little donuts, sometimes used for shipping, those things are polystyrene. But it's a foam. It's mostly air. If you dissolve it in acetone, it just dissolves down to nothing. All the air escapes. It's kind of a cool thing. So anyway, all these plastics are kind of fascinating on one level. So this is an example of another type of way to make plastics. It's called a condensation polymerization reaction. And what you want to do here is you want to take usually different kinds of molecules and put them together. So while polyethylene is basically CH2, 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 and you might have different, side chains of it or something, but it's all the same. Well, here you can actually combine different functional groups. So notice the A and the B down there in the lower right. Those are going to represent different types of chemicals, and they're going to combine in chains, but the properties of these plastics will be quite different.
Ethylene glycol and terephthalic acid can react with each other at both ends of either molecule. The reaction produces a molecule of water and allows the bonding of the remaining molecules. If many such molecules are available to react, a polymer chain of polyester is produced.
These kind of reactions always have some kind of leaving group. Now in this example, water, H2O, is the leaving group. And so what chemists will do is they'll collect the water, and you can back calculate then how many transformations have occurred, how many A's and B's have come together, because each time you do that, a water molecule is kicked out. But anyway, really cool stuff. Contact lenses are made this way, nylons are made this way, pretty powerful stuff. Here's an example of the actual chemicals. Instead of saying A and B, you can see what it is. In the upper left-hand corner, that's terephthalic acid. So in the middle of the C double bond OOHs, you've got a benzene ring, and that reacts here with ethylene glycol. Ethylene glycol has a CH2CH2. Ethylene glycol is a diol, as two alcohol groups we talked about earlier. But anyway, they'll combine, so then you've got a benzene ring between the carbonyls and a CH2CH2. That's going to have a lot different properties than if you have just CH2, 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 etc. Anyway, lots of examples. The lower right-hand corner, I found this reaction. It's how they make Kevlar for bulletproof vests. I thought that was kind of interesting. Anyway, lots of different kinds. And again, we're not doing justice to this wonderful field in this little bit of a lecture, but it is kind of cool, and at least that way you know what's happening. Polyesters, again, all around us. A lot of our clothing is polyester, with jackets and shoes and shirts and stuff like that. Soda bottles are made from it. Lots of films and stuff. Lots and lots of uses.
When adipoyl chloride and hexamethylene diamine come into contact, hydrogen chloride is given off and a polymer is formed. This polymer is commonly known as nylon 6,6, one form of nylon. The number 6,6 indicates that there are 6 carbon atoms in each of the monomers.
Check out how you can just pull that stuff off. It literally makes like a sheet, and then you can wrap it around the cord. It's an amazing reaction. This is actually a pretty famous reaction. This is one of the first of these that was made. Nylon 6,6 is kind of cool, and this is another condensation polymerization reaction. Now, to make this nylon 6,6, they use these two chemicals. You don't have to know these names: adipilyl chloride and hexamethylene diamine. And then that nylon 6,6 is all the part there in the parentheses. You can see the N right there. So you've got whole bunches of these things just over and over and over again. The leaving group in this case is hydrochloric acid. So again, you can collect the hydrochloric acid and figure out how many transformations have occurred. The 6,6 of nylon 6,6 refers to the 6 carbons in the A and the B group. That's where that comes from. It has no other references to the 6,6. Anyway, it is really cool stuff. Lots of uses for polymers. So for example, Teflons and fabrics I talked about earlier, but also a lot of the bottles we use for soft drinks, styrofoam. If you ever use plastic wrap at home, saran wrap, that's a type of a plastic. Contact lenses, absolutely important. So again, it's around us all the time. Like here in my office, I have the iPad pencil, which is plastic. A lot of the computers is plastic, and it's just amazing. It's around us all the time. Bubble gum is actually a type of copolymer. It's got 2 different pieces that come together to make it, which is kind of fun. And slime is another use of polymers. So there's fun uses and stuff as well as practical uses. And again, they are around us all over the place. It's just something we kind of take for granted a lot of times. Recycling of polymers and plastics, I think, is critical. The numbering system that's used, you may have seen this on bottles and materials 1 through 7, tells the type of plastic. So number 2 and number 4, those are both polyethylene. The high density polyethylene is number 2, and the low density polyethylene is number 4. Those are usually pretty easy to recycle, as well as number 6, the polystyrenes. The 1, 3s, and 5s are a little harder, but often you can find sources for them. Number 7 is just basically all the other types of plastics, and those can be kind of tough to recycle, but still places will take them. I highly recommend that you check out your local recycling options because, again, plastics, 150 kilograms per person per year of these are made, and that's a lot, all right? And there's a lot of people, so that's really a lot. So the more you can recycle, of course, the better. This is just one example of a recycling guide that I was able to find online. You can find your own guide. So for example, we use Waste Management, WM, for our local place where I live, and they have a list like this too. You can find a list like this for where you live. Okay, so that's it for chapter 21. Again, this chapter has been short and sweet. It's all on the organic chemistry. And again, I want you to focus more on the naming. Focus on the alkyl groups, how to build the alkanes, what an alcohol is, stuff like that. I also threw in the ester and the amide because they sound too much like ethers and amines, and I want you to know that. I want you to be prepared. And finally, you can ignore the reactivity. That's just more than we have time for at this point, but it is important, and if you take organic chemistry, you'll definitely see some of that in the future. Okay, thank you so much for joining me here. I really appreciate it, and I hope it has been helpful. If you have any questions, reach out to me. Have a great day.